what I'm trying to do is here is you have same contents and same stuff in a PowerPoint, and here is I explained the MNIST and things like that. And in order to run the Python, you have to import some of the key libraries here. NumPy and Matplotlib, of course, is because we're gonna do the deep learning, so it's TensorFlow here. And here, how you get the MNIST data set. And here, as you can see, the total number of, sorry, give me a sec. Yeah, sorry about that. And I'm gonna continue on. So here, as you can see, let me see. That's the, as you can see, this is the total number of training data set in MNIST. I mean, number of training images in and digits in the MNIST data set. And the shape, as you can see in the shape for the inputs is not 28 by 28. It's I mentioned several times it's flattened out, so it's 784. And for the outputs, because they store it in one hot encodings, that's why we have 10. Here for the testing data set, we have, I said, 10,000, right? And just plotted one of them. That means it's a fifth image in the training data set. And as you can see, for each element of the matrix or array, I will matrix zeros, and some of them are like here. So I guess the maximum number value is 1. It's already, I think it's normalized. And what I can see is it's a shape. So I need reshape it. So for this one is that for fifth data set, I reshape it to 28 by 28. It will be stored in the image. And let me plot that. So it will be, this is the image that you can see. And what I can do is I can just say, I don't know, it's the first one. Use it like that. And since it's not the, so we have to put it in the grayscale because it's not usually let me get rid of these things. So it's in order to make sure that, because this is not a colored image, so use the gray options to plot it like that. And for the outputs and the labels, it's like, let me go back. It was, what was the 8, right? So as you can see here, this is 9 and 8. So in order to, we're gonna use np.argmax. So that's how we get the corresponding the labels. And there's a method is next batch, means if I want, I will get just one of them. And if I want to get 2, so it will extract it in among the training data set. So that's how I define, say, like that. Like you can get 5 of them, right? So it's as I mentioned this, we're gonna use the next batch method for the, because we're gonna do mini batch stochastic, mini batch gradient descent. That's why we need the batch size. So we do it, and to implement it for the classification problem, to classify the MNIST data set in artificial neural net. So the way that we're gonna do is we're gonna these will be the inputs. So the number of input neurons gonna be the 784 with the hidden layers in the middle and the 10 output neurons. So this is gonna be the exact structures that I'm going to implement it. I think you already last time. So remember, it's 784, 110. And we're gonna do batch gradient descent with this kind of scheme. And basically it's a gradient descent. And let me see, we did that and we already did that. And this is how we, so probably I will say just 784. And there will be the hidden. Let me change it. So let's say we have give me any number that you guys wanted to try for the number of hidden layer.
75.
74? 74? Is that what?
Yeah.
Okay, so let's so it's 74. And that's how you, so for now, I need to define the weights and bias. So weights. And for the keys, hidden, probably, and the outputs. That's how we're gonna use TF variables. And here we have to put shape and type. We don't have to put just shape, is good enough. And see the we need, initial values. Initial values, that's what we need to do. So this TF, we're gonna use random, normal. And that's the shape and STD. I don't think we need that. And that's input and hidden. Okay. And I'm gonna do, so it's hidden and output. To repeat it to bias. That's how we define it. And we need placeholder for X and Y. That will be the TF dot placeholder. TF dot placeholder. You see, and here TF dot, that's the type, we need a float. And we need to define, that's the batch size because we don't know yet. So probably it's same as inputs. And it will be the output. That's how we define the placeholder. And for the models here, type it again. You already know, but the model, we need X and weights and bias. Return. For hidden layers, we actually, let me We're going to do matrix multiplications with the x and weights, and hidden layers with and plus. We do biases and hidden layers. I mean, here a little different, but it's pretty much the same. And do hidden will be TF, and then let me see what kind of. Let's do. We have values and what about? Let's try sigmoid in this case. I just want to use trying the different one. The output, it will be that, but we have hidden as input to the output layers, and it will be output. It will be output. That's how we build the models. And the optimizers, let me see. Predict values will be because we have models. That's for the placeholders and biases. And the loss will be, we have, and this is a multi-class, so it will be softmax, cross entropy, and logics, and labels. This labels is true answers, logic is gonna be the predict. Because we do mini batch, so we have to do reduce loss. That's how we define it. And for running rate, that's for the value of alpha is something you have to, I mean, you have to do try and errors, and this one I just found that in I mean it's a reasonable thing, reasonable numbers. For optimizers, train Atom optimizers with running rate, and I want to minimize loss. Optimizer has no, oh, there's some typo. Minimize.
You forgot the E. I.
Minimize. Okay. And let's use a different optimizer here. We can do, what kind of optimizer we have? You guys, anything that you guys in mind? Gradient? But gradient. Stochastic?
It's with J caps, high caps. Yes, you just press it.
Did I pass? Gradient is okay, so let's do that. So I mean, I'm just trying to different one. That's the, and let me see here how we say the batch size and 50. I mean, just with 100. This how, and another one is we need to open the sessions and to initialize it, and we have to for epoch and range with iterations. Here, for each iterations, we need to get from MNIST, train, and the next batch. And how many? Because we have a batch size, it will be train X and train Y is gonna be. Now we need run it optimizers with feed dict. Okay. Placeholders in X, I'm gonna plug in the X and in the Y placeholders, I'm gonna do train Y. Okay. And I'm gonna skip the, so that's how we, now it's running. So I guess, let me see, I don't plot it. And for the test, we're done with the train the models from the training data set. What I can do here, I got, in the test data set, I got 100. What I can do, it's gonna be run and predict, feed, dict. Now I need X, I don't need Y. Okay. And there will be np-arg max my predict, but in because it's in not here in this way. Let me see. The label is gonna be like that. The accuracy is 8%. Something's wrong. Let me go up. Let me see. Did I make any mistakes, or let's do more. I do more iterations, and let's see, 10%. Something's wrong. That's why we actually need these kind of plots to see. Let me see. For each iteration, the loss is still high. Okay, so let me see. We need, let me get, I think it was the original one. Let me run it. What's wrong with my loss? Did I make any mistakes? Do you guys know? Let me see. Okay, let's use the Atom optimizer. Sure. So I changed the. Now I'm using the optimizers and like that, and try to run it. Now it says, as you can see, the loss, it gets smaller, right? It's less than 1. And to evaluate it, now it's the accuracy is around 87, which is, I think it's okay. And to do that, I just got to evaluate it, or to see what kind of things. I got just one of them, and that was in one of the random pick in the testing data set. Is obviously it's 0, right? And if you look at the probabilities, here is, let me see, 0, 1, 2, 3. This one, 3, 4, 5. Somehow we have 40% of prediction in say the A, and I think this is kind of 5. I don't know why. Let's try a different one. This is 5, but this is 7. But here you can see it's still we have 55% of the chance of saying it is 5, but we have 43% of that this believes that it's 5. It's 7. Obviously it's 9. We have 91% that it's saying that it's I think it's 9. Okay, that's what we did last time. Any question on how do you implement it or how do you use the Jupyter notebooks like that? I think you did similar things in the previous homework assignment, so I believe that you already know how to use it. And let's think about the advanced contents in EuroNet. So today I will do the advanced stuff and think about the nonlinear activation functions. And here I introduced the sigmoid or the tangent hyperbolic things in this on ReLU. And in the title, the key thing that you should remember is the vanishing effect in the gradient problems. What is the vanishing gradient problem is it's following. So as more layers using certain activation functions are added to neural net, the gradient of the loss function approaches zeros, making the net hard to train. What do you mean by that? As I mentioned here, if that's it's kind of multi-layer perceptron structures, and this one is function of this and the function of this and the function of this and the function of this. So it's a composition of functions. So in order to compute the gradient or whatever, then you have to use chain rules. It's a backbone of backpropagations. But the problem is this it's multiplications. If we have 10 layers, that means you have to do 10 multiplications. And think about, you suppose you use the sigmoid functions as your nonlinear activation function. Then this one is the plot. As you can see, it's the values from 0 to 1 and smooth and differentiable, which is good because I think that you remember that the motivation was that it's starting from the perception or step functions, and one of the biggest disadvantage of step function is it's a non-differentiable, so we use the sigmoid functions. And if you take the derivative, that means the slope of the sigmoid functions. As you can see here, it's almost zeros, and here it's almost zeros, and here that's the maximum slope. That's the maximum slope. So, and the red, the curve is derivative of a sigmoid. That's the exact plot that I made. But as you can see, the derivative of whatever, it's a at least you can see that it's I mean here. So it's the derivative, the partial derivative, the value of itself it's less than 1. Then you're gonna do 10 multiplications. Suppose you have 10 layers, then eventually the value is gonna be extremely small. Extremely small. So no matter what kind of thing this, you will see all of them, the gradient is approach to 0. That means you're not going to have any updates on omega, right? This one is we call it it's a vanishing problems, because the gradient or partial derivatives or gradients, all the values we're going to vanish. So that means it's hard to update omegas. That means it's hard to train or hard to learn. All of them the same meanings. Right? And this is it's a severe problems, especially for deep learning structures. Deep learning means that if you have very deep structures, that means you have more layers, then the vanishing effect, the gradient problem is gonna be more severe. So it's hard to update or hard to learn or train all the omegas, weights and bias in. So that's the problem. So the idea is that they come up with the ReLU activation functions. So it was a great improvement compared to the historic, sigmoid or tangent hyperbolics. And this guy is from -1 and +1, and the sigmoid is probably it's like that. It's pretty much this, just it's scaling and shifted. And I would say this is a sigmoid. But tangent hyperbolic, the ReLU function it's a little different. This is the ReLU functions. When x is positive, this is y is equal to x. When x is negative, the outputs of ReLU function is going to be zeros, right? And that's, of course, because of that, it's nonlinear. But actually, this is a piecewise linear functions. If you're just looking at the positive, it's a linear. And if you're just looking at the negative, it's a linear functions. But if you see the whole graph, it's a nonlinear functions. Here the slope is 1, and here the slope is 0. What about here? What's the slope at the origin? What do you think, guys?
Infinite.
Okay, then let me ask, do you think this, this is continuous functions, of course, but what about do you think this is a differentiable or not?
It's not.
It's not. So it's not differentiable in principle. Right? But when you compute it, say in the numerical way, there's almost 0 chance that the value of x is exactly equal to 0. It's almost 0 chance. So it's okay. And even in the worst case, say somehow it's exactly 0, then what you can do, you don't have to know, but what the computer does behind will be add some epsilon values. It could be positive or negative, it doesn't matter, right? Then it will be, if it happen to be positive, the slope is 1 or it's 0, right? But that's gonna rarely happen. So there's some so to fail safe. And the good thing about it is if you take the derivatives, it's 1 and 0. It's like on and off. So, because that means I'm doing a lot of multiplications of 1, so there is no vanishing effect. And if it's negative, that means it's gonna turn the the wire off. It's disconnected. Right? So that's it's a derivative is not vanishing. Because of here, some of them are disconnected, so the network is gonna be dispersed. Another great benefit of using ReLU function, ReLU nonlinear activation functions in it. Right? So there is no like the vanishing things because we have here. Okay, and another one is, so that's why if you think this is if you think your network is deep, and probably like it's recommended to use ReLU functions instead of tangent, hyperbolic, or sigmoid functions, because of you can kind of prevent the vanishing effect and problems. And another thing that it's batch normalizations, and let's see what is it. The batch normalization is the technique to improve the performance and stability of the artificial neural net. And the idea is extremely simple, right? So we're gonna normalize the input layers by adjusting and scaling the activation functions. I mean, if you take a look at this one, is see in each neurons, the scale might be different, and I'm gonna normalize it. So everything is gonna be between, say, it's in certain values. Okay. So each iterations we will do batch normalizations like that. And one of the biggest advantage of that here, as you can see, let me see. Let me plot it that one. So for if you think it's a sigmoid functions, let me see. So the function is gonna be that's a sigmoid, and the slope will be like that. And since your value is like here, it's let me change the colors. Here it's extremely small. So if you do batch normalization like that, that means you're shrinking all the values around here. Right? So derivative of that is it's a smaller than one, but at least it's at the, I mean, here. So that's why we is trying to put all the values around the origin. So it's kind of to avoid the vanishing effect as well. Okay. And another reason is that if you have all the inputs and neurons, the neuron values that are in the different space, this is kind of normalizing its behaviors. And another reason that the batch normalization is good, because you guys remember here when I talk about the step size alpha in special, if if you have, it says you have this kind of contours, then each iterations, this direction is very stiff. Okay, so in this direction is it's not stiff. So that's why if you have the same step size on the all the directions, that's some problematics. That's why I think we that adaptive. That's why adaptive is alpha is better than, I think that's, you guys remember it. And if you do batch normalizations, that means you're scaling down. So to make these things, we're trying to like it's gonna be the similar scales in all different directions. So in that case, since there's no, so that's why we can have it's gonna be the better, even though we have a constant step size or learning rate, we're gonna have better optimization scheme. Okay, so it's because in the batch normalization we do scaling on each neurons or in each, I would say, each features or each unit. That's the another big advantage of using batch normalizations. And again, let me see. So this is how we do. So in each iterations we compute the mean and the variance and normalizing it using this. But actually you don't have to worry about it, because actually you're not gonna do this by yourself. We're just gonna use the batch normalization command or functions or method in TensorFlow. But you have to remember that what kind of situation that you need to use a batch normalizations to improve your performance. Right? Say you didn't get the high enough accuracy that you expected it, and you have to improve you have to change your, either you have to change your network or you have to change your optimization scheme. You can think of different running rate, or you can think of different optimization solvers, or you add some kind of the batch, whether you have to decide whether you want to implement it, the batch normalizations or not. But at least you have to get some conceptual ideas of what kind of behaviors that you expected it if you implement the batch normalizations. Okay? And I think it's gonna be the last topic, and the title is a dropout. And I already mentioned what the regularization is. It's basically if you do not have enough data set, probably you're gonna suffer from the overfitting problems. And in order to avoid that, regularizations, that's something that you're supposed to think. And the first thing is that you have to increase the data set. That's the first thing. But if it's restricted, or you have some limitations to get more experiment, to get more data set, the next thing is that what was the, so it's get increase number of data set. And probably, I think it was the early stopping, or add regularization and term in your objective functions. And the last one was the dropout, but I didn't explain it at that moment, because the dropout is very special method, specialized in artificial neural net. Let me think about this. I mean, this one is a regularizations. You add in total cost, if you have measure of fit and you have measure of magnitude of the coefficient. So this is kind of that you saw many times, and that's the typical way of implementing regularizations. Here it's for big data set, or So this is first, and second thing is data augmentations like that. And this is kind of tricky, but it's extremely effective for data augmentations. And you can shift it and rotate it and rescaling it, all those kind of things. Yeah. And it's another one was the early stopping, and you just predict the training errors and the testing errors to stop when at here, because we kind of notice that here it's starting to overfitting, as you can see, and it's different regularization techniques in deep learning. This one is going to be, this is one of the most interesting type of regularizations. It produced a good result and is most frequently used. It's extremely easy to implement it. So the idea is that suppose we have this kind of, so here will be that kind of structures. And each iteration, you're gonna randomly select some of the node or neurons or unit and remove them like this. Then you train them in that iterations. In the next iterations, and forget about this, and starting from here, randomly select another neurons, okay? Then trained. That's what dropout does. And you might wonder is why this kind of thing is going to help us or acting as regularizations. Because you can think of as ensemble techniques of machine learning. Because, sorry. So say this one was the first iterations, and the second iterations probably, say, you get different the nodes out, then your networks and things like that. So say you have say it's like 10,000 iterations, then you can think of as you have 10,000 different neural net, and you do ensemble of them. Then it's ensemble is kind of acting like smoothing effect. So it's gonna be the it's gonna be the regularization behaviors or effect. And you have to, let me see, you have to, so effectively different architecture at each training epochs. And so in original models, you say you have like that. And in here, what you can do is that in tf.nn and drop out, and you have to define what's the rate, drop out rate. That's the probability that each element can be dropped. Right? If you say it's 0.1, each iterations, the 10 out of all the neurons gonna be dropped, out. So here, this will be the networks. And let me see. So for the training, there will be the rate. For the testing, so when you train the models using dropouts, you define the rate, and all the networks some of them are removed. For the testings, you have to keep all the elements and neurons, because you're doing the ensemble of them. So that's something that you have to remember. For training, some of them are gonna be dropped. And for testings, you kept all of the elements. So let me see. Any questions up to this point? Because today, I mean, so what I did is kind of discuss the advanced materials related to neural network. What I can do, let's see here. Let me see. What I want to do here. I got how many data points? I got 10 points, and there we have it's a regression problem. And suppose we have this kind of, we have 4 hidden layers with these number of neurons, and I define all the weights and bias for each layers and the placeholders and for X and Y, and build the models. And since this is a regression problems, now you have to notice that you have got the predict values, and you just take the square. And since this mini batch, we have reduced means and use the Adam optimizers. And let's figure it. Let's do. And it's gonna take. Okay, so let me see. And these are the loss that I can get. And here, that's the output of. As you can see, it's overfitted, right? So let me go up. With this kind of the structures, we have 10 training data points, and how many unknowns? How many the parameters that we need to estimate it? So it's how many?
Can you repeat how many?
So we have 10 data points, right? 10 training data set. That's the given problem. It's a regression problems. And as you know, if we have 10 unknown parameters, I mean, how do I say? So for the regularization problems, 10 training data points, if you have 10 unknowns, I can make it the errors on the training data set equal to 0, right? But here in this case, I got so many parameters, way more than number of training data points. In this case, it happened to be 10. So here I got 30, I got 3,000, like 10,000, 30,000, I got 30. That's the parameters, the number of unknown values or the coefficient that I need to estimate it using the neural nets. So of course, it will be overfitted. So what I want to do, I want to, let's say, implement batch normalizations, and I need another placeholders, whether this is a training or not, because in batch normalizations during the training process, I need to batch, but in let me see, batch normalizations. This one. Let me discuss the dropout first. because I'm talking about the regularizations. And here is dropout. This is the syntax. I need to define the dropout rate. And there's the placeholders P. See that? And here, as you can see, and these are the same as the previous one. And I need to add this one is with the, in these layers, with these probabilities, I'm gonna drop layer out. Okay, and in the next layers, this one's gonna be the inputs, right? I'm just repeat these and run it. And for the build models, I need P as well. P is the okay. And during the optimization process, let me see here, I got to optimize it using the feed dict X. In the placeholders, I put the training data set, and Y, I put the training Y. Here, I assign 20%, the elements gonna be dropped out during each iteration. That's how we implement dropout. So it's running, and let me see. So I got the loss, and here this is the thing that you guys to remember it. Now I want to evaluate it. I want to evaluate it, and to evaluate it, to get my predictions, and I put in X in the placeholders, and this is key. Now I got 0 dropout rate, because when you do evaluations, I'm not gonna do dropout. That's how I implement it. And this, I mean, this is not a good example, but and you can see some of the regularization effect over here. I can say this is not the perfect example, but I want you to show how to implement dropout in here. So remember that. Any question on dropout and on implementing the dropout in TensorFlow? Okay, if not, I will go back to mini batch problems. This one is something is not intuitive, but this one is how you use it in normalizations, and this is the only changes here. You do batch normalizations. So you got here and you do batch normalizations. After that, you do sigmoid functions or any kind of nonlinear activation functions. And whether this is, you have to know in the training process, you will do batch normalizations. Okay. And this is pretty much the same. And now this one is something, but you can just use that one to get all the collections and key to update it. Got it. And these are all the trainable variables, and to get collection of that and update it and use here. And for the training process, is that true? And for evaluating, it's a false. That's just like dropout. You have to remember it. The training process and the evaluation process, whether the batch normalizations dropouts, it will be on during the training process, or on the other hand, in the evaluation process, both of them gonna be off. That's the key things that you guys are supposed to remember it.